you have midterms back. So, same deal as last time. If you don't like your score, redo it completely, send me the solutions. So, kind of an easy task, really. It's just a way to go through, make sure you understand everything. You know, maybe try to do it again all by yourself, see if you can work through the calculations and write it up nicely. Take a picture of it, scan it in, send it to me. This will be due by the final return as well. So I'll just say due with the final. Reduce due at final. So if you can, please send me one email with everything. So just keep in mind, I've got a whole bunch of you. If you send me your homework, 2 homework assignments, 4 extra credit, I think there's like 3 or something like that. Send me some extra credit, final, midterm. Don't be surprised if I'm human. So, and I lose track of something in there. So I see roughly 100 emails every single day. And so getting 1,000 from you guys is going to make my life difficult. So one email with all these attachments in there, but you can turn these in as well. I'll give you half of the differential back, and so it's a good way to pad your score. Also, just to let you guys know, I don't recurve anything. Like I always hated this, right? It's like you do extra credit, and then all of a sudden your curve is based off of the extra credit, but that doesn't make it extra anymore. So I've seen that in classes, I hate that too. And so it's just additive. And so I'm going to take your grades. What I'm going to do, once I get your final and all of that, is I'm going to go through, I'm going to grade it, I'm going to look at it, I'm going to tabulate your grade, and then I'm going to go back and add all the extras. So I'll have my thresholds in place where I think the dividers are, and there'll be clean dividers between groups of students. Once I put everything together, I'll look at it a number of different ways. So I'll look at your midterms, look at your final, put that stuff in, see that your homework is okay, and I'll start stratifying. Lots of different ways to see where you lost points. And if it happened to be that there was one problem on one test where you lost a significant number of points and it made all the difference in the world, I don't hold that against you guys if everything else is in order, if you've been diligent throughout the semester. And I'll give you some sympathy. Otherwise, I usually think, well, it was because you don't ever come to class, I've never seen you, I don't know who you are, you didn't turn in any extra credits, and I look through your homework scores and I see they're late, that sort of thing. Then I'm not inclined to provide the extra sympathy and say it doesn't matter, and I don't move the threshold or whatever. I hope that's all very reasonable to you guys. So. Lots of ways to get an A in this class. I understand test-taking anxiety sometimes gets to all of us. Scores, again, they're all over the place. So I'll just show you the histogram of the midterm 2 scores. They look like that. Let me try and make this a little bit bigger so you can see the axes. Normal. So I don't mean Gaussian. I mean this is regular in a class like this. So bimodal distribution. Typical thing, probably most of your grad classes are supposed to be like that, unless it's incredibly easy. So a typical grad class is usually bimodal. People in field, people that want to become, have that card carrying ability, be a theoretician, understand all the underpinnings of everything. I want to point out in this class, we're not really teaching you how to carry out an analysis. We're giving you all the properties of estimators and tests and things like that, and that's what this class is all about. And so I will say that on some of these exams, scores are all over the place. Some people miss stuff on just kind of the definition. They would leave out something. A very common mistake is not to tell me that a loss function is a non-negative function. So that'll mark you off 2 points there. Something like that. It's not a big deal. You can fix it in an instant, and you'll remember to put that stuff in there. And so all of these small things, when I look at it, I don't think you don't know what you're doing. I think you know exactly what you're doing, and you just need a minor correction. And so that's what these scores are supposed to tell you. Just go reflect. Some of you had a harder time with calculations, did well on definitions, you did okay on the midterm, but make sure you can do these calculations as well. So it's a lot easier to think about the second time around, I think. Any other questions about this distribution? You want to know the mean? I mean, we could estimate it, right? It's like, it's somewhere around here. It's really not a very good description of this distribution, right here. So probably around there. Where's the median? It's probably like just it might be a shred lower. So, but we can look at those. They're in the 70s. They're pretty typical. So I did leave you with all the little nitpicky things, the -2s here and there. No big deal, just fix it up. So if you want the points. If you have a 92 or an 86 or something like that, that's relatively high on this exam. And so if you're like, oh my goodness, I got an 86, darn it, and it really upsets you, don't do that to yourself. Just go back, decide whether or not you want to make those corrections or not. It won't make much of a difference in your grade, because I suspect you're probably going to get an A in class. So especially with the final, it's going to be take home, you should do well on that. So I am pretty considerate when I look through all of this stuff. And for the most part, I thought everything I saw in here was easily correctable. Cool. So the mean, maybe the mean, we can't help ourselves. 72. Median, maybe that's higher. Say 76, 78. So, a little bit of skewness in there, not that surprising. Again, some of these people, some of you guys really know this stuff. You study all the time, and I'd love to get all of you there, but I understand all the time constraints in the different priorities. This class is difficult, and a challenge is putting together all the concepts. So we'll just keep repeating it, hopefully give you a little bit of practice. And if you take my inference class in the fall, the Bayes class, I do a comparison of Bayes against all the classical stuff as well. So we'll keep it in there. Hopefully sync home some of these points that we're kind of flying through. Okay. Any other questions? I'll hand these back at the end. If you want to rifle through it, panic, try to debate over your score, whether or not you get an extra couple points, why don't you hold off for a minute? So, and talk to me maybe at review session or after Wednesday or something like that. And so I'll just make a note, we'll do a review tomorrow. At 5:30. Business as usual. I don't think it's so necessary to spend the time on yes, no, maybes, because it's a take-home exam, and I'll give you several days to do it. So I don't think that will help, but if you want any clarification or to go through the exam or anything like that, it's a good place to do it. Okay, lots of nuanced issues. I would imagine if you're really into this stuff, there's lots of questions. I'll try to provoke some more questions today. Okay, that's enough on midterms. I'll pass those back at the end. Somebody just remind me I'm bound to forget right at the end. I'm still me. It's amazing, isn't it? Okay, let's go through this. Unbiased tests. I've alluded to what this is before. So let me just write it down. A test is unbiased. And so I'll just say this test has power function B, so I'll just call it B theta. If this condition holds, so B theta prime is going to be greater or equal to B theta double prime. If theta prime is in the alternative, and theta double prime is in the null. So what it's saying is that a test is unbiased if the power is greater in the alternative space. So let's remember what the power is. The power is the probability of rejecting the null. I'll say H naught. And then you end up looking over various values of what the truth could be compared to the null. And so it's a whole function over speculative truths. We want the probability of rejecting the null to be higher in the alternative. And so I think that makes sense. It doesn't always happen. And so that's a real problem. So just as an example in that binomial example, if I had said, when we were testing if theta was less than a half, in the binomial we solved 5 values, we got to flip the coin 5 times. And so if the total number of successes was 1, and I rejected under that situation, if I picked that to be my rejection region, the test would be heavily biased. And so the test is biased if you include any values for rejecting in 0, 1, 2, and 3, and that's because the probability we're testing was thresholded at 1/2. And so I'll let you think about that a little bit. So those tests that we concocted last time, they were all unbiased. So let's just look at another example. Let's see which one I wrote down. H naught. Theta is less than or equal to theta naught. So we studied this example before. Xi, we're going to come from a normal distribution with mean theta and variance sigma squared. And for this example, we assumed that we knew what sigma squared was. Everything here was IID. We wanted to test this versus the alternative. So this is a one-sided test right here. In our power function, it's just the probability that, make sure I get the direction right, x is going to be greater or equal to some value. I guess I call this k. I think they call it c in the book. And they're recycling the notation c. This was going to be plus theta naught minus theta over sigma squared over n. Is that? It's obviously wrong. Sigma over root n. So that's the standardized form. And so that was our power function, and it looked like this. Theta naught was there, and our power would be increasing. So this is 1. This thing is asymptoting into. Probabilities don't go bigger than 1, and they don't go smaller than 0. And then at theta naught, we were able to compute this value. So how do I compute this value? I plug theta naught into this equation. So under the null hypothesis, I'm checking to see if that thing right here, our test statistic, oh, and I should say this is x bar, really. So that's what we're testing, is this x bar. So that's what x represents here. It's just a random variable. And so this thing, we ended up calling alpha. So this is the null, and this is the alternative region. This is the important value, and I'll try to exemplify that in a couple minutes. The p-value in the Neyman-Pearsonian thing is not important. It's whether or not it ducks below alpha. And so the size of the p-value in general is meaningless. It doesn't mean anything. Now, I sympathize a little bit in the one-sided case. It obviously corresponds to this probability. And so it is ordered, and maybe it means something to you in this example, but if you compare it to the sharp p-value, the p-value itself doesn't mean anything. And this is the big debate that Fisher and Neyman and Pearson got into. And I'll tell you a little bit more about that debate and what they're arguing about. So here's our power function right here. Oh, in this thing, I shouldn't call that x bar. This was going to be z. So that's my standard normal. So sorry about that. It's x bar minus theta divided by sigma over root n. So that was just our standardized value where I'm conditioning on that's the truth right there. That's that same theta value, and I'm comparing to theta naught. When theta naught is the truth, that's a theta naught right there. That's usually the value that we compute when we're computing a p-value itself. And then I'm just looking at this extra term. So if that were theta naught, this would be 0. And this value is what we use to calibrate the critical thresholds. So if we were doing a one-sided test, you might be thinking of those values like 1.68. If we were doing a two-sided test, you might be inclined to use 1.96. If you use 1.96 in the one-sided test, you're testing at the level, the 2.5% level. So just to give you some examples. This test is obviously unbiased. So these probabilities over here are smaller than those probabilities over here. So that's what this says. So this power over here is larger than this. This is a monotonically increasing function. That's important. So that's what a power function is. I'll just point out that for the hypothesis, I'll just write this in. Note, for testing, I'm just going to change the roles of the alternative and the null. This is going to be theta greater or equal to theta naught. H alpha, theta, and I should plug my equal sign in there. That has to be in the null because that's where we actually plug in the test. So this is going to be less than theta naught. The power curve is very similar. You can derive this using the name and Pearson criterion, but this is going to just reverse this sign right here. Sigma over root. And so, very similar thing, the power function ends up looking like this. Theta naught, this is going to come down like that. This will still be alpha here, and it's just reversing the direction. And this is still asymptoting in 1. So it just reverses the direction of the power curve. And I don't have any great problem with this sort of analysis. If you report that p-value, I think it's fairly reasonable. So this is also an unbiased test for testing that. I will point out, if you use this power curve for testing this hypothesis, you'd be extremely biased. You'd be doing exactly the wrong thing. And so all of your decisions I would probably just flip. I think you're a perfect predictor if I just, every time you say to do something, I do the exact opposite. Then I think you're a good predictor. Okay, so that's stuff we already know. I want to just point out what a p-value is. So a p-value. We've all heard of these things. Bless you. Somebody give me a definition. Somebody asks you to find the p-value real quickly, your life is on the line. No problem. Okay, let's make it more fun. You win $1 million. I don't have it to give, so you'll have to take my IOU. It's never going to happen. But what's the definition of a p-value? Anybody feel ambitious this morning? I can wake up at any time, on any day, in any state, and make sure I get this right.
believe that you observe something has extreme as the value you just observed, given the null hypothesis is true.
That all sounds good. So it's the probability of observing your data or more extreme data. Of course, we have to understand what data we're talking about. So usually we phrase it in terms of the sufficient statistic or something like that. But it's the probability of your test statistic being more, values being more extreme or greater than what you actually observed, given the null hypothesis. So that's important. So given H naught, this is the probability of your data or more extreme. This is the part that's a violation of the likelihood principle, the more extremity part. And we saw that in our example when we studied the likelihood principle and we looked at the binomial. Experimenter 1 was assuming things were binomial. And experimenter 2 was thinking that things were negative binomial. And when they summed over the more extremity, that normalizing constant came in and it changed their p-values. And so this is the part that people say, why are you looking over things that are more extreme, i.e. they're implausible, they didn't happen, is a proxy to reject the null hypothesis. And I kind of get it in terms of a limiting sense. We look at more extreme things, and we think about limits, and then we think about what to do with them. We do it as humans all the time. I will say it's not a direct contradiction. So the way we're taught this is a contradictory statement. We condition on the null, and if our probability of our data lives in a region of low probability, then probably the null is incorrect. And so, but this isn't a direct contradiction because you're looking in this region of more extremity. It's not just your data. So it's more extreme data, which defines the rejection region. And the rejection region is defined by the null hypothesis. And so just as an example, so I'll say, let's just test this one. Beta naught versus the alternative, beta is less than beta naught. So this is my second example right here pertaining to that power curve. And we're going to do the same thing. Xi's are normally distributed with mean theta, variance sigma squared, and we'll assume this is known. If it's not known, then we would move over to the t-test. And if you're a Bayesian, they would do the exact same thing, that they would be using a t-distribution by integrating over that precision parameter. So at least the Bayesian and the non-Bayesian do agree on which distribution they use. I'll show you next time what they do is extremely different though. So in some cases they actually do agree with each other. And so here's what you normally do. You compute the test statistic. And so our test stat that we would look at, usually we end up looking at this thing, x bar minus theta naught sigma over root n. Our test stat is really x bar, but I'm just rescaling everything. And so, and I'm going to look at a normal 0, 1. So this is a standard normal. And I end up looking at this value, Z, right here. And then I compute this tail probability. If you want to see that the analog where I don't standardize everything, this is equivalent to this normal right here, where this thing is going to be sigma over root n. That's my standard deviation. And then I'm going to end up looking at x bar. So that's our test statistic. And I would compute this probability right here. This is the standard normal. These are exactly the same probabilities. So that probability and that probability are equivalent to each other. It doesn't take too long to convince yourself of that. So you look at your test stat, and no surprise, your test stat has to do with the minimal sufficient statistic that you end up looking at. I could look at all my xi's, and they could live in some high-dimensional space, and I could think about where they needed to live, so that this condition was equivalent to computing this probability. It's much easier if you think about things through the minimal sufficient statistic, because you don't have to think about this high-dimensional space, but they would be equivalent to each other. So right there is the p-value. And that's what we end up computing. I just want to make a statement. P-values in general, I think you all know this, but this is exactly what you're doing when you do the Neyman Pearsonian thing. So the Neyman Pearsonian thing for rejecting, it's equivalent to the rule that they teach you in Stat 101 class. So Neyman Pearson and I'm going to make them slight here. And I'm going to overstate something, and I'm going to say it the way probably your Stat 101 teacher said it to you. So Neyman Pearson says, so I'll make an error here, and then we'll correct the error. Compute p-value. Well, okay, so you might do something like this. Compute your test stat. In our case, it was either the z-score, x bar, it's all equivalent, just depending on which distribution I plug everything into. So then I'm going to compute the p-value. If our p-value, and I'll call this p star, whatever that is. So in our case, p star would have been this thing. If p star is less than or equal to alpha, we'll reject. Otherwise, fail to reject. Okay, so my Stat 101 teacher is pleased with me because I said it the way they indoctrinated me with. Didn't say except, it would have marked me off 10 points for that. So I wouldn't do that. So I don't really buy into that. Okay, so this is the idea. So Neyman and Pearson actually didn't say this, but this is what everybody ends up doing. So Neyman and Pearson, they devise a procedure for a uniformly most powerful test. And so p-value in general, it doesn't tell you which test statistic to look at. And so you can devise your own. So I could look at other test statistics. I could look at z-squared or something like that. So if z has something to do with more extremities, z-squared does too. So why not just use that, find the probability distribution of z-squared, it's going to be some chi-squared, and then I test more extremity on that. You could do that. It has the exact same semblance of contradiction, but it's not uniformly most powerful. So Neyman and Pearson are giving us a procedure for getting the test statistic that provides the uniformly most powerful test. You can imagine all kinds of test statistics for testing things like this right here. So instead of looking at x bar minus theta naught, I could have looked at x bar divided by theta naught and thought about, is that close to 1? So x bar minus theta naught, is that close to 0, is similar to x bar over theta naught, and that's a different test that you would end up computing. And so that's not uniformly most powerful. It's doing that. So Neyman and Pearson tell us how to get the test stat. So this is through the likelihood ratio. So through the LRT. So you need to have a full model in hand to do that. This is a little bit elusive in practice because data doesn't come with model in hand. And so we end up trying to, a lot of times, tailor things so it looks normal. I don't really love that game. So they're also assuming you have the correct model. So then you compute your p-value. If the p-value ducks alpha, you end up rejecting the test. Under any case, regardless of what likelihood, which test statistic you use, if H0 is true, the p-value itself is uniformly distributed. Let's just prove that and then make a few statements about this. Have that sitting on the board without writing a more extreme thing. It's just so important. So I don't want somebody to come in and look at my video halfway through and see that I didn't have that written correctly. The p-value. So what's the p-value thing? What we're looking at is the cumulative distribution. So in those pictures I just erased, we're just looking at the cumulative over a sufficient statistic from the model. And so I will make a statement. So this is a fact, I won't test you on this, I don't really need you to know it, but there's a statement in the book. It's attributed to Carlin and Rubin, and what they say is that when the power function is monotonic, is in the cases we just saw, then the Neyman-Pearson test is going to be equivalent to thresholding the sufficient statistic. So that kind of makes sense. So I believe it. It's likelihood ratios that we're looking at. Likelihood ratios have the sufficient statistics in them. So the monotonic thing says that one directionality of everything is right, and so it's probably going to boil down to thresholding the sufficient statistic. And we can see it in this example. If you want a proof of that, they provide it in the book, but I'm not going to go through it. So it's kind of intuitive that it should be true, but if you want a formal proof, look at the book. Okay, so what we do, a p-value is a cumulative distribution. I'll just remind you of that. P-values are cumulative. Yes. So i.e. we end up looking at something like this. If we were doing this right here, we would have looked at the cumulative over z. So we would have been looking at f of z in all of this. So that's just this normal density right here. And then I'm just going to compute this up to my z-score. And that's my p-value. All stat 101 stuff. So this was centered at 0. And this was 1. If I didn't standardize everything, I'd be doing the equivalent thing with x bar, and I'd be looking at a cumulative distribution. So that's just integral of f of z. And I should point out that this is being conditioned on h naught, that theta is equal to theta naught. So that's the cumulative distribution that we're plugging everything into. I've conditioned on it right here. So dz, and I would end up computing from negative infinity to z. If we were doing the other test right here, I'd be looking at the other tail. So I'd be looking at this tail probability. So again, all stat 101 stuff. So maybe I'll write this down as FC. Okay. So let's just look at this. So we want the probability distribution of our p-value. And I'll say that's less than or equal to some dummy argument, t. So I want to know what this probability distribution is of the p-value. This is going to be the probability distribution of fz. You can let that substitute that for any symbol. That doesn't need to be the standard normal thing. Whatever your test stat is, you're going to be plugging that in, and you're going to be looking at its cumulative distribution. So less than or equal to t. I want to point out that this has been conditioned on the null hypothesis. That f right there. So this is computed under H naught. So this is true. Probability Z is going to be less than or equal to F inverse H naught T. I need to justify real quickly that I can invert that function. So why can you invert this? It's that cumulative probability that we're looking over. It's monotonic. It's increasing. Be careful. Obviously, if you're looking at something that has a big discontinuity in there, and then you end up averaging over it, that cumulative distribution will be rising, and then it'll be flat for a while. And so you'll need to redefine your inverse function to deal with that. But I think you get what I mean. You can grab any value in that interval. So, and I'll just redefine the inverse using that. So the inverse exists, or at least some generalized form of it. The inverse that we could all agree on exists. So what's this probability distribution right here? This is specific to Z. So it's the same cumulative function that we're using right here. That's how we compute probabilities over whatever that test statistic is. And so this thing is equal to F of F inverse H naught of T. So let me just point out, this is going to be under some, this is going to be under either one of these. This is going to be either H naught or some value in the alternative space. So I'm either going to condition on theta naught. Now I will agree that in this test right here, theta naught is a range of values. So you're taking the most extreme one, you're taking that maximal probability to compute everything. So you're checking everything at theta naught itself. And so if this was theta naught, let me write it over here. So if H naught is true, i.e. the data that you generated came from the null hypothesis, then the p-value is this thing. F inverse, conditioned on theta naught, Z, and this would be H naught as well. So if the true distribution of Z was really generated under the null hypothesis, then this cumulative function for Z is checking it under the null hypothesis. So I have F inverse, they're the exact same functions. That thing is going to be, oh, my bad, this is a T. Does it say T? Good. That's the way it should be. So I know how to do that. That's T. And so just going back over here, if I said this thing is equal to T right there, then I know there's only one distribution. And if I check the probability of being less than something, is that something? I know what distribution does that. So if I say the probability of something is less than 0.7 and it's 0.7, but the probability of something being less than 0.1 is actually 0.1, I know what that probability distribution looks like. It's uniform. So this means it's uniform. i.e., it's uniform. I want to point out that under the alternative, HA, and you'll have to pick a value for H alpha. There's a whole bunch of them. But you would end up picking that value, plugging it in right here, inverse T under the H naught. These are not inverse functions. They won't knock each other out. But you can show that this is a decreasing function. So the farther H naught gets from H alpha. So the key point in Neyman Pearson testing is that This is uniformly distributed if the null is true. So what that means is if I compute a p-value, and I'm checking to see if it ducks alpha, so this criterion right here, and the null is true, that was actually a draw from a uniform distribution. And so the type 1 error rate in that case is alpha itself, whatever you've calibrated. So what's the probability that your p-value ducks alpha if the null is true? It's alpha, because it's uniformly distributed. Let me write that down. So what all this says, here, I'll write it here. So the type 1 error rate is equal to alpha. So this is really important. And this is why it happens, because the p-value under the null is uniformly distributed. Hopefully you guys know that. Type 1 error rate is alpha. What is Nathan and Pearson doing for you? Under this fixed type 1 error rate that they computed by calibrating that k parameter in the power function, if they ended up doing the Nathan and Pearson thing and worked with that test statistic, they would also be uniformly most powerful, so they would be minimizing that type 2 error rate. All admirable goals. So kind of makes some sense. I kind of like it. So keep that in mind. Let me show you that the p-value in general doesn't mean anything. So let's consider the big culprit test, the sharp test. So consider testing H naught, theta is equal to theta naught, versus the alternative, theta is not equal to theta naught. I've already made a lot of comments about just the nature of this test, that I don't think it makes a lot of sense. But I can kind of understand Fisher wanting to test this. Is it just something different from theta naught? Can I say that? I really wish they would have designed an interval test. And they would have shown how flawed that was under the Neyman and Pearson thing, because I think you should be testing it in an interval. I'll say more about that next time. We do study the interval test in my base class, and I do show you what the uniformly most powerful test is, and it's really whacked. So enough on that for right now. So if I ended up using this power curve right here, that we ended up getting by testing that first one-sided hypothesis, we'd get this power curve, and it would be biased. So that wouldn't work out very well. And so this power curve would be biased because this is part of the alternative space, that's part of the alternative space, and only that one little point is the null space. And so the probability in the alternative region is lower than that. So this would present a biased test. And there's really not much you can do, because where we got this from is we ended up looking at something like this. And we ended up thresholding it. And we got this monotonic sort of behavior because of the nature of the test. And so that was all monotone. The nature of the test is just this one-sided sort of thing. And so it doesn't really lend itself too well to testing this. So if you ended up computing the other power function, those are supposed to look like reflections of each other, you would also be biased if you use this power curve right here. So there is no UMP test for this. You can't construct it. So both of these power curves pertain to biased tests. So you can't do that. So no matter which direction you test, you've got some biased test, and they don't like it. So here's what Neyman and Pearson said to do. Really, they were following Fisher's procedure for computing a p-value. But Fisher didn't go through all the rigorous stuff to say what does the p-value size actually mean. Neyman and Pearson were trying to help him out. So what they do is they unbias the test. So we're going to force a test to be unbiased. And here's how they do it. So here's theta naught. Here's our earlier power curves. So that's what we had before. This was power. And they end up just taking this bit out. So they say the shape of this curve lends itself to a uniformly most powerful test, but it's biased. And we're just going to get rid of the bias by doing that very rigorous mathematical thing. Let's just erase it. And you can kind of see what happens right here. That this would be alpha. We would need to recalibrate alpha. So if I was doing the 5% test over the one-sided thing, I might have 1.68. If I wanted to make this alpha 5% for the bias test, I would need to change that constant to 1.96. And it would be changing the height of this thing to bring it down a little bit. So you just recalibrate there. So this right here isn't exactly the same as that value right there. They're going to be calibrated differently using a different K. And so this is unbiased because the power here is smaller than it is on either side. But a lot of what Neyman and Pearson had said just vanished on us. They really were talking about this one-sided thing, thinking about monotonic power curves, and everything kind of made sense until all of a sudden you throw it into this, new restricted class where I just get rid of the stuff that unbiases it. So what's the big mathematical theory for unbiasing it? You just erase that part of the power curve. So forget it. I like the way that the shape and the theory of the other stuff, and so I'm going to cram this into the same box. I'll have to tear the box to do it. So, and we won't tell anybody, we'll just tape it up and pretend that nobody noticed. So that's kind of how I feel about this. So this is an unbiased test right here. But I would say it doesn't share the same properties of something that has a monotonic power curve. So I just want to point out, for the sharp test, write that here. So let's say you were testing H naught, theta is less than or equal to theta naught, versus theta is greater than theta naught, and got a p-value, and I'll call it p star. So I went through everything, I computed the p-value, it's p star, whatever p star is. But if I test it, so I'll just say this thing right here, I changed the tail direction, so that's our p-value over here. So I changed it from the other one I drew. The way I always know this is right is I always chase the alternative tail direction. So if it ever confuses you which way you do this, good luck explaining it to somebody. What all this is actually doing. So I think there's a lot of conundrums in all of this thinking. But if you end up testing the two-sided thing, so I'll call that Z, what they're saying to do is you would also compute this probability right here, the other tail direction. So our corresponding p-value, so if I test this, theta is equal to theta naught versus this thing, the described test is going to compute these two different tail probabilities, and that's why you'll hear it called the two-tail test. So our p-value would be p star times 2. So it'd be twice as big. What I want to do is just point out to you, the p-value itself is not a measure of the null hypothesis. So Fisher accidentally said that. So the p-value can be taken as a measure of how correct the null hypothesis is. So small p-values put a smaller measure on the null. Large p-value put a large measure on the null. Fisher's absolutely incorrect about that. And you can see that just right here. So think about how big this set is. It's very big compared to that one. So if the p-value was a measure of the null hypothesis, the p-value for testing that should be much smaller than for testing that. And in fact, it's twice the size. So the p-value size itself doesn't mean anything. What I really want to point out is that people that are testing one-sided tests, doing one-sided tests or simple versus simple tests are in a very different setup than when they test this. This is a totally different thing. So I don't have a harsh argument about one-sided test or the simple versus simple. I think they're close to things I would do. I'd probably have a little bit of nuance difference, and I'll describe that next time. But if you were testing this right here and you use the name Pearsonian thing, you cram everything into this unbiased box, and you start interpreting the p-value is a measure of the null hypothesis, it doesn't make any sense. This should not get 2 times bigger than that. So this is what people are talking about when they say p-values are non-additive and incoherent. So the size of them does not correspond to anything in general. So when Nathan and Pearson came in and said it's the alpha level is what matters, that's the only thing you report. Fisher didn't like that because he thinks it shouldn't be this sharp decision, it should live on a continuum. Let's pick up next time. We'll just rehash their debate. I'll tell you what Bayesians do, and then that will be our class. So I'll see you next time. I'll see you tomorrow with the review session at 5:30, and if I don't see you there, I'll see you on Wednesday. Thanks a lot, Jason. Exams. Jennifer?